Volcanic eruptions, just the words themselves, they conjure up images of utter chaos and devastation, don't they?
Oh, absolutely.
We've seen cities buried, global air traffic brought to a complete standstill, even climates thrown, into disarray for years.
Indeed. And the largest among them are, well, they're more than just local disasters. They're potentially existential threats.
Right.
So understanding the immense forces driving these events isn't just scientific curiosity. It's really vital for our future, for our ability to prepare.
Absolutely. So today, our deep dive is going to take us thousands of kilometers under our feet into this hidden world,
Way, way down there. It's quite a journey.
where scientists have uncovered something truly, well, astonishing. Huge continent-sized structures sitting right there within Earth's mantle, and they've given them a wonderfully descriptive nickname, haven't they?
They have. They're calling them blobbies. It's short for BLABs, which actually stands for Large Low Shear Velocity Provinces, a bit of a mouthful.
Definitely a mouthful.
So blobbies definitely stuck. But, playful as the name is, these things might actually hold the key to Earth's most powerful volcanic events.
And that's really the core question we're tackling today, isn't it? How these hidden giants could be directly linked to the most, well, unimaginable eruptions, and what that connection means for potentially predicting the next big one. For this deep dive, we've pulled from the latest seismic imaging, essentially using earthquake waves, right, to create these detailed scans deep inside the Earth.
Exactly. It's much like how medical imaging works, like an ultrasound revealing internal structures.
Okay.
And we're pairing that with historical geological data, put them together, and they're painting a much clearer, sort of more cohesive picture of what's really happening inside our planet.
So this isn't just theory.
No, not at all.
Yeah.
It's actually answering some long-standing questions volcanologists have had about how the deep Earth truly operates.
And crucially, it seems to be forging a direct link between these deep structures and the eruptions we see on the surface.
That's the key finding.
So our mission today is to try and uncover exactly what these blobbies are, how they fit into the whole Earth system, and maybe most importantly, what their existence means for our ability to forecast future super eruptions.
Can we get better at forecasting these immense events? That really is the million-dollar question, isn't it? And the research, well, it provides some pretty compelling insights.
Okay, let's start peeling back those layers then and uncover this hidden world. Because for the longest time, the standard picture, the one you'd see in textbooks, described Earth's lower mantle as, well, fairly uniform. A smoothly flowing layer of hot rock.
Yeah, it seemed deceptively simple looking back now.
Right.
But then came this advanced seismic imaging, using those earthquake waves to get incredibly detailed scans deep inside. And suddenly, that smooth image was just completely upended.
Gone.
It revealed a far more rugged, dynamic landscape down there than anyone had really imagined.
Rugged is a good word, definitely not smooth. I mean, imagine finding two enormous structures, each roughly the size of a continent, rising up like these immense hidden mountain ranges from the very base of the mantle.
Staggering.
It's like discovering new continents inside the planet.
The scale is truly mind-boggling. And volcanologist Annalisa Cucchiaro and her team, as they studied these structures, gave them that now famous nickname, BLOBs, the blobbies.
The blobbies.
And what's crucial about them is that they seem compositionally different from the surrounding rock, and they appear to play this really central role in deep Earth processes.
So they're not just passive lumps sitting down there.
Not at all.
Finding something that massive, completely hidden for so long, that must have been one of those huge aha moments in science.
Oh, it was a major discovery, absolutely. And the crucial insight, as you said, is that these blobbies aren't just passive lumps. They seem to be actively fueling Earth's most dramatic surface events.
Okay, so what kind of events are we talking about here specifically?
We're talking about the supervolcanoes, those really massive eruptions. Scientists have known about mantle plumes for a while, these sort of super hot, buoyant columns of rock
Right.
that are thought to rise from deep within the Earth, supposedly punching through nearly 3,000 kilometers of mantle rock to feed huge eruptions. But for ages, the big mystery was, where do they actually start? What's their precise origin point?
And this is where the blobbies come into the picture.
Exactly. Cucchiaro's analysis, bringing together all the available seismic and geological data, points very clearly to one conclusion. These deep mantle plumes rise directly from the tops of those blobbies right at the base of the mantle.
Wow. So the blobbies are essentially the source points, the launch pads.
Precisely. Think of them as the start of these giant magma highways connecting the deep interior right up to the surface. It's a really strong, direct connection they found in the data.
Magma highways, that's a powerful image, a direct pipeline from Earth's deep interior. So, okay, this connection isn't just theoretical, it sounds like a tangible system they've identified. And that immediately raises the question about forecasting, doesn't it?
It does, if we can map these deep structures accurately. I mean, could that give us a way to predict where the super eruption might actually happen? That's the crucial implication, and it's exactly what the researchers started to investigate.
How do you even begin to test a hypothesis like that? It seems incredibly difficult.
Well, they took a really fascinating approach.
Yeah.
They basically went back in time, about 300 million years ago to the late Carboniferous and early Permian periods,
Okay.
and they meticulously mapped out the known locations of giant eruptions from 3 completely separate neological data sets from that specific era.
And when you say giant, you mean those truly climate-changing events.
Exactly. The kind powerful enough to significantly disrupt the global climate, maybe even trigger mass extinctions. We're talking serious Earth-altering stuff.
Okay, so they mapped those ancient cataclysms.
And then, this is the clever part, they compared those locations to where their models predicted plumes would have risen from the ancient blobbies back then, 300 million years ago.
And did they align? Was there a match?
They found a statistically significant alignment. It wasn't just random chance. The locations of those past super eruptions lined up remarkably well with the predicted paths of plumes rising from those ancient blobbies.
Wow. So this connection, it isn't just a modern phenomenon. It seems to be a fundamental process that has been happening for hundreds of millions of years.
That consistency over such a vast geological timescale is incredibly compelling evidence.
Yeah.
It really strengthens the case that this is, a fundamental process in how the Earth works.
Which then brings us to another long-standing puzzle for geoscientists, right? Do these blobbies just sit there fixed at the base of the mantle, or do they actually move? Are they like stationary anchors, or do they kind of drift around with the flow of the mantle's convection currents?
Yeah, that's a huge question. It makes a big difference in how we picture the mantle's dynamics. So how do they figure that one out?
Well, Cucchiaro teamed up with geoscientist Nicholas Flement, and they ran these incredibly complex computer simulations, supercomputer stuff.
Modeling the lower mantle, specifically, and stretching the simulation back 1 billion years.
1 billion years, that's just an astonishing time frame to model.
It really is.
And the results were truly fascinating. The simulation showed these blobbies aren't stationary anchors at all. They can actually migrate, they drift.
Precisely. They wander.
Mm-hmm.
And crucially, as they move, they actually tilt the plumes rising from them.
Tilt them, so the plumes aren't necessarily rising straight up anymore, like a chimney.
Not necessarily, no.
Hmm.
If the base moves, the plume tilts, and the significant consequence of that is, well, the eruption spot on the surface isn't directly above the blobby anymore.
Okay. Which means it might pop up dozens, maybe even hundreds of kilometers away from where the plume actually originates deep down.
Exactly.
So this mobility, even if it's happening slowly over geological time, it really changes how we think about volcanic risk today, doesn't it?
It absolutely does.
Mm-hmm.
It implies that a region we might consider relatively stable today could, over geological timescales, shift into a plume's path. How does that wandering affect where we draw the hazard zones? It adds this whole other layer of complexity to our predictive model.
Indeed. This mobility makes prediction harder in some ways, maybe, but potentially more accurate if we can actually track that movement. And it highlights a fascinating paradox, doesn't it? The same deep processes that pose this immense threat from volcanoes also seem to provide unique opportunities.
How so? What do you mean?
Well, these huge eruptions are obviously incredibly destructive, a catastrophic risk, no question.
Right. But they also create unique economic opportunities. Think about kimberlite pipes, for instance.
Yes.
These are these vertical, sort of carrot-shaped volcanic structures formed by incredibly deep and rapid eruptions, bringing up material, famously diamonds, right from the mantle.
Diamonds, yeah, everyone knows about those.
And it turns out these same deep volcanic processes also concentrate rare earth minerals, things vital for modern tech like neodymium and lanthanum.
The critical components we need for green technologies, right? Like wind turbines and EV batteries.
Exactly.
Yeah.
So the very same deep processes give us these vital resources that we increasingly rely on and simultaneously pose this immense threat. It's a really profound paradox of our planet.
It really is. But the hopeful side of this, maybe, is that by putting all this together, the deep imaging, the surface geology, the computer simulations, we might actually get significantly better at forecasting these events.
That's the clear goal, yes.
Yeah.
Scientists hope to refine eruption forecasts, potentially even getting years of advanced warning for certain types of events.
Years. That would be transformative for preparing communities, wouldn't it? Truly a potential game changer for reducing risk and saving lives.
Absolutely. And it's just remarkable to see how Kukiyara's team is actively tying all these different threads together. The seismic images, the plume models, the eruption records, they're building this cohesive picture piece by piece.
Yeah.
It truly drives home how dynamic the deep Earth is and how hazards right here on the surface trace back to these processes happening thousands of kilometers down, completely unseen by us.
It reminds me of what Nicholas Flan, who worked on the simulations, said. He put it, this research really cracks open questions that have long plagued scientists. Are the blobbies stationary or mobile? And how do they relate to giant volcanic explosions?
And it feels like we're finally starting to get some concrete answers. These are definitely major steps forward.
So what a journey this has been today, deep into the Earth's interior, unraveling these pretty surprising connections between the deep Earth and the surface.
It's fascinating stuff.
Okay.
And it seems abundantly clear now, doesn't it, that researchers are forging this direct, tangible link between those hidden, continent-sized blobbies far below.
And the powerful, potentially world-altering volcanoes we see, and let's be honest, often fear right here on the surface.
And what this deep dive really highlights, I think, is just how rapidly our understanding of the mantle of these deep Earth dynamics is actually growing. It's thanks to all this new data and these incredibly sophisticated models.
Exactly. And with that growing understanding comes, well, the hope for a far better ability to prepare for and maybe even anticipate Earth's most formidable displays of power.
Which really leaves us with that big final thought for you, the listener, to maybe mull over. In this age of incredible technology, we've got satellite monitoring, supercomputers running these massive simulations.
And all the tools we have at our disposal now, yeah.
Can we finally get to a point where we can truly anticipate and maybe even find ways to mitigate the impact of the next great volcanic eruption?
It feels like the ultimate goal, doesn't it? And maybe, just maybe, this kind of research, connecting the deep Earth to the surface in such detail, is bringing us a significant step closer. It certainly seems to be making the path ahead a bit clearer.